Welcome to a next episode here. So we are continuing with the separable differential equation, and that's another example here. Remember, we're not just solving and finding the solution in this class, we're analyzing the solution. And it's an example of such question. So if you read this question, it says solve this following initial value problem. So you have a differential equation which is going to be separable, and it has a initial condition which is y of 0 equal to 1. In other words, when x is 0, y is 1. So the point is 0 comma 1. So the graph has to go through this point 0 comma 1. And you're not done. The question also asks you and determine the interval in which the solution is valid. Because given an arbitrary function, what is the domain of this function, right? In other words, they're asking what is the domain of this solution? For what value of x this solution makes sense? It's a function. It has to be a function, right? And it actually also gives you a hint. And of course, in this type of question, you need to use some type of graphical utility like GeoGebra, or if you know some other mathematical software like MATLAB or Mathematica or Maple. Please feel free to graph and explore the solution. In this, in this case, in my case, I'll simply use GeoGebra. It's very intuitive to use. So first, let's solve. So let me copy the differential equation. So I'm going to replace y prime by dy dx equal to 1 plus 3x squared over 3y squared minus 6y. Of course, you can write as c, you can simply cross multiply. So if I cross multiply, I have a function of y times dy equal to, I have some function of x times dx. So this is indeed separable. Take the integral of both sides. The left hand side with respect to y. So the integral of 3y squared is y cubed over 3 minus 6 times the integral of y is y squared over 2. I'm going to add c on the right hand side. Only one side we add c. I explained that before. The integral of 1 is x plus, I copy the 3. The integral of x squared is x cubed over 3. And then here I add plus c. And that will be the general solution. Let's simplify a little bit. I can cancel out 3. I can cancel out 3 here. 2 goes into 6 3 times. A little bit of simplification, so I get y cubed minus 3y squared equal to x plus x cubed plus c. And that will be my implicit general solution. Y is not solved in terms of x. In this case, we will not go for explicit because it will be difficult because you have a cubic equation. Although we have a formula for the cubic, it will be quite difficult. So we'll skip that, and we don't have to do this in this case. So this is implicit general solution. Now let's use the initial condition to solve for C. So the initial condition is y of 0 equal to 1. So that means when x is 0, y is 1. So let's substitute x equal to 0 and y equal to 1. So I'm replacing y by 1 and x by 0. And writing everything down so nobody get confused. So this is simply 1 minus 3, which is minus 2. And this side, all I have is c. So my c is negative 2. So go ahead, I can replace this c by negative 2 here. So that will be my specific implicit solution. So let's do that. So I'm going to copy everything else. That will be the specific solution. And of course, it will be still implicit. I'm replacing c by -2. And that will be my final algebraic solution here. So that will be a specific solution. And again, this is again implicit, right? We're not making it explicit. Now, but the question also asks you, what is the interval where it makes sense? What is the interval, right? What is the interval of definition of, or what is the domain of this function? What is the domain? So let's actually look at it in GeoGebra and see how the graph looks like. So I'm going to start with the general solution. So again, going to GeoGebra. Okay. So let's start with the slider C. And then I'm going to put the general solution, y cubed minus 3y square equal to x plus x cubed. I always like this GeoGebra and different types of picture we get. So this, okay. So at this moment, my c is 1. And you can see there's the picture. Okay. Let me actually change the color. So you can go to the setting and change the color. So let's do red. And that's a solution of this differential equation, but of course it does not satisfy the initial condition, right? So if I move my c, for each value of c, I get a solution. A beautiful, beautiful animation, right? Okay. I can actually increase my value of c, so I can get a more detailed picture. So let me make my slider from -10 to 10. Let's do that. So now you get a very good picture. Okay. And actually you can use this play button to animate. Wow, I like it. So for each moment of time, if I freeze, that's a solution to the differential equation. That's another solution of the differential equation. That's another solution of the differential equation. So each one of them, for each value of c, I get a solution. But look at our initial condition. My initial condition is that when x is 0, y is 1. So let me put that point 0 comma 1. Okay. So that's my point A. So we know, of course, we solve algebraically and we get c equal to -2, of course, right? But let's actually play and see at what, and look and also pay attention to the c value, right? For what c value this graph is actually goes through this point A, 0 comma 1. So it's coming close, coming close. So maybe I do a little bit slowly by hand. Okay, so right there is on top of that point, right there. Okay, so a little bit, yeah. We know it's -2, right? Algebraically, so geometrically is always, um, an approximation. It's not like it's not like a absolute, because you're looking it by your eye, and you are more or less trying to approximate. So that's my picture right there, right? So that's my implicit specific solution. So if I go back, that's the equation. So that's the one, y cube. So when I replace c by -2, that will be my picture here. We can see it here. My c is -2, right? That's the equation here. So that's the specific solution. Now, if you look at carefully here, the whole thing is not a function, of course, right? Because it does not pass the vertical line test. Okay, so let me actually copy that in our note. Let me copy that in our note. Okay, so let me actually copy this here. So if you look at this solution here, the whole thing is not a function. because it doesn't pass the vertical line test, right? So for example, if I draw a vertical line, it intersects more than one, right? So it's not a function, of course, right? But if you look at it carefully, this actually can be divided into three branches, three functions, right? So if you look at here, so one is this much, right? That is going to be is one branch, one function up to this here. Okay, so that's one function. Another one is starting from here and goes to this much right there. Okay. And finally, the other function or the other branch, you can have it from, let me use a different color, maybe green, from here to here. Okay. So you can divide this implicit equation into three explicit function, right? You have three of them. So one, two, three. So you have three branches. So use this word branches. Okay. But out of these three branches, only one of them goes through this initial condition, right? If you look at the initial condition, is that's the branch we're interested. The other two branch does not go through this initial condition. So that is our function we're looking at. So we can forget everything else and just look at that part, that much, right? And just by looking at this picture and in the GeoGebra, you can see the domain of this function, right? If you look at the domain of this function, right, is from -1 to 1. So that is the domain of this function, right? Or that is where the function is defined. And of course, the GeoGebra helps you to do this here. So the answer here, just by using GeoGebra and the computer, the interval of definition or the domain of our function for our branches, right, is x is between -1 and 1. Okay. And that will be the domain of this specific branch that satisfy our initial condition. Of course, it is possible to solve for y and get an explicit equation of that branch, but that will be quite complicated because I have a cubic equation. But of course, you can do it using other types of mathematical software like Mathematica. But we are not going to do that. Now, they give you a hint. Look at that hint. So to find the interval of definition, look for the points where the integral curve has a vertical tangent. So integral curve is like the graph of the solution. Vertical tangent means the denominator is 0 when the slope become infinite, right? So if you look at the vertical tangent, that is going to happen when the denominator is 0, right? And if you solve for y, if you factor out 3y, you get two solutions, y is 0 and y is 2. And look at this picture, going back to our picture, right? Okay. So actually I'm going to use here, right? And look at here, right? So if you look at this picture here, my y is 0 and y is 2, right? So let's take a look at it. Y is 0 and y is 2. So when y is 0, right? So that's my y is 0, right? Okay. And then when y is 0, I get this point. And when y is 2, which is this one, right, I get this point here. So it's between these 2 points. But again, if you don't want to follow the hint, it's okay. You can simply use the GeoGebra and get your answer. So that is okay. Thank you. Bye bye. And make sure you always remember that you can do it.